Some of those experiments were based on the predictions of the Scottish physicist James Maxwell. In an historic set of equations, Maxwell had theorized that visible light was an electromagnetic disturbance with a specific wavelength, and that other electromagnetic waves existed as well. In 1886, Hertz noted tiny sparks jumping from a discharging induction coil to another coil nearby. That seemed to indicate the presence of electromagnetic waves. With his assistant, he set about systematically investigating the phenomenon and constructed an apparatus comprising a kind of transmitter on the left and a receiver on the right. Hertz edged closer to the transmitter. At a distance of about 2 meters, sparks started to jump across the gap between the receiver's conductors. And Hertz was sure he knew why. The sparks were the result of invisible electromagnetic vibrations, which were radiating like waves through space and energizing the receiver. Helmholtz was the first to be informed of the sensational results. His comment, "Bravo." It was Helmholtz, too, who published details of the experiments. Hertz continued his research with patience and vigor. On one occasion, he wrote to his parents,
"I'm working like a factory hand, repeating every step 1,000 times over. I spend hours on end drilling one hole after another."
He sent regular progress reports to his father, who was by then a member of the Hamburg Senate. If it was true that electromagnetic disturbance took the form of a wave, it should also be susceptible to reflection and interference. At the end of 1888, Hertz set up another experiment in the lecture theatre at Karlsruhe. His aim this time was to show that electromagnetic waves could be bounced off a metal reflector. The entire length of the room was needed for the experiment because Hertz's apparatus, the transmitter on the left and receiver on the right, could only produce radio waves with a wavelength of around 60 centimeters. A sketch showing how the apparatus should be arranged in the room. Benches at the rear served as supports for the 2-meter-high zinc reflector. The experiment had to be conducted in darkness to enable the scientists to make out the faint optical phenomena at the receiver. Sometimes Hertz and his assistant found it took hours for their eyes to adapt to the dark. The transmitter was switched on. The electromagnetic waves struck the zinc plate and were reflected, at an angle equal to the angle of incidence, back to the receiver. Then, Hertz's assistant stepped into the path of the beam. His body absorbed the waves and spark action at the receiver ceased. In this and later experiments, Hertz confirmed the characteristics of electromagnetic waves. One characteristic, which is very important today, is interference, which can either disturb or reinforce radio or TV reception. A wave reaches our aerial. We receive a signal. It's joined by another wave, an indirect or reflected wave perhaps. If the two waves are in phase, reception is improved. But if they're out of phase, they cancel each other out, and reception is severely impaired. But back to their discoverer. Now a scientist of international renown, Hertz moved in 1889 to Bonn University. Here he finished writing the scientific papers subsequently published under the title The Principles of Mechanics. Hertz himself, however, didn't live to see their publication in 1894. He died shortly before his 37th birthday of insidious septicemia. From his deathbed, he wrote to his parents,
"If anything should happen to me, do not mourn. Be proud and think of me as one of the chosen few who live but briefly, yet long enough."
Science paid tribute to Hertz by naming the SI unit of frequency after him. 1 Hertz means 1 cycle per second. Ordinary alternating current from the mains has a frequency of 50 Hertz, which corresponds to a wavelength of 6,000 kilometers. Low-frequency waves are 10 times shorter. Next in the spectrum are radio and television frequencies, followed by radar in the microwave band and heat radiation in the infrared range. Even shorter wavelengths are found in the ranges spanning visible and ultraviolet light, and at the furthest end of the spectrum are X-rays and gamma rays.